Okay, so last week we have already discussed the several testing standards for the ESD, including the HBN, MN, and CDN, and we also talk about we can use transmission line pulsing. That's what we call the TLP, which is a very useful way. The pulse can generate from transmission line, and then also the pulse signal is very convenient for us to diagnose for the ESD values, and so it's very useful that we can use a TSP to understand the ESD mechanism rather than directly use HBN, NN, or CDN testers. And next, we will start to discuss what would be the concept for the ESD protection. So the good ESD protections should be triggered under the low ESD current, and also to be able to clamp the voltage of the protect IC at the clamping voltage, which must be lower than the IC's breakdown voltage. So this is a simple schematic to illustrate how these ESD protections are working. So we have our main protect device here. So we want to avoid the latch up in this device. So therefore we have to place a nearby ESD protection device, and then we want to make sure that this ESD device can have the latch up happen earlier than the main protect device. So that's the idea. So once we have the electrostatic discharge event happen, so we want to make sure that this ESD latch up event will mainly go through this ESD protections device rather than our main device. So the condition will be that we have to make sure the latch up can be happen earlier than the main protection device. So that's the idea of how we actually do the ESD protection. So we all knew that under a certain ESD event that there could be the latch up event will be triggered in the main device. So what we actually do is that if there's a protection ESD protection device nearby, and then the latch up happen earlier, then the ESD charge can be discharged through this protection device. So here is several scenarios here. So if we look at the first one, this is our protecting device. So we all know that if we don't have any ESD protection, once we have enough higher voltage here, so we will have the latch up will happen. And then the idea is simple. If we can have the nearby ESD clamping, and that can happen earlier for the latch up, so that means that once we have the ESD voltage go through here, but this will happen earlier, so therefore all the charge will go through this ESD clamping, and therefore we won't influence our protection device. So therefore if this can happen earlier, then we won't have to worry that the latch up will trigger in our protected device. So in this graph, the main idea is that the latch up event in the ESD clamp should be always happening earlier than our protect device. then the main protected device. So that's a typical ideas that how we do the ESD protection. And there's several different cases here, especially the first one is okay. That means this is one that okay to make sure that our main device won't suffer the ESD failures. And then the last one, these are the several different scenarios here. So then the second one, case 2, will be the protect device fail, because the protect device will happen earlier for the electric event than the ESD clamping. So these are the 4 different scenarios. So you can look up later by yourself. And by consider how do we make sure that our ESD clamping is good for the ESD protection. So TOP is an effective method to analyze the ability of ESD protection device. So here is a comparison of the waveform coming from the different testing methods here. So we have the testing method for the HBM, human body model, and also the TOP here. So we can see that in this case, with a short pulse, by using the short pulse, the self-heating in the device is limited. So the IV characteristic can be measured to much higher current level. That's more realistic for the ESD discharging, which is this one. So these are the TOP here. And then the information using the TOP is compatible to loss due to the capacitor discharge of actual ESD event here. So that's one empirical result that the 1 amp TOP with a 100 nanosecond will be equal to 2000 volts capability for the HBM, and also the 200 volt for the MM here. So that's the empirical equation we can try to compare with the TOP versus the HBM and MM. Okay. So now, if we talk further, we will start to look at that for the ESD testing. So ESD testing, if we test on the package device, there will be the several different methods. For the first one is the I/O, input output pin to power pin, pin to power pin, pin to pin, and also the VDD to VSS, and also the square pulse testing, and also the charge device mode. So we will explain one by one. So here is an example that how we do the input output pin to power pin. So the idea is that we will stress each pin. So we will do this is how the typical package device look like. So we will test for each pin and try to look at and then ground it as a VDD or VSS. And then the idea is that we give the ESD pulse here and try to look at the ESD capability between this pin to the VSS. So we try to test for each pin versus the VSS capability. So that's a purpose for this I/O pin to power pin. So this is the PS. So the pin to the VSS, and also we have the pin to the VDD. So it's a similar. It's a similar, so we need to test for the ESD capability here. So similarly, not only for the positive PS or PD, but we also need to do the negative. So here is a negative ESD voltage test between the pin to the VSS, or negative voltage from the IO pin to the VDD. So that's the first one. We do the pin to power pin. And also, we need to also consider the pin to pin, which is stress one input output pin and grounded another input output pin, and then also we put as a power for VDD or VSS as a floating, and then we also have the two-way. One is a positive, for example this one we give the positive pulse here, and also the negative, give the negative pulse here. So that's a typical testing procedure for the ESD. And also we need to test for the power pin to power pin. So from the NAND of this testing is very clearly understand this is a stress at the VDD or VSS, and then we grounded at the VDD or VSS. So that's also another typical testings. And also we have this square pulse testing. So we stress a pin the DUT as a one pin, and then we try to give as a high current as possible. So that's very similar to our TLP. So this is exactly for the TLP pulse method. So we give each pin as a one TLP, and to look up whether there is the ESD values or not. And also we have this CDM, the charge device mode here. So what we do is we consider that the charge is at the substrate, and then we discharge at any pin here. So we have the charge from the substrate here. And then we discharge from any pin. So that's for the CDM mode. So that's try to understand that the influence coming from the charge that accumulated. So you have a certain substrate that you place your sample on top of this substrate, and then the charge on the substrate might be immediately discharged and then to your device. So therefore we have to test this CDM as well for the ESD capability. So to have a very good ESD protection, we need to consider the several devices that can help us to have the ESD good ESD capability. So therefore, in the following, we will introduce several very often used ESD protection device. The first one is what we call the TVS dial, which is the full name is the transient voltage suppressor dials here. So first of all, probably you have already knew that the typical characteristic of a dial is look like in this way. We have the forward high current turn on, and also reverse we also will have high current turn on. So therefore we can consider to use this region and this region as a ESD protection. So this is a range of the operation in the event that has a ESD strike here. So which means that if we place this TSV dial here next to our protection device, and therefore suddenly if there's a ESD voltage, ESD strike, no matter for the positive, this will turn on. So therefore you have high current go through here, right? So your diode is turned on. So that's a very basic characteristic that how we actually use the ESD. So but nowadays still very often we use this way. We just place a diode next to our region we want to protect. So once this has a positive, this will turn on. So therefore you have high current will go through this diode, and rather than will go into this our main device. And also if you have a negative as well, so because you have a negative, so negative will leverage this characteristic, so then the diode can also have the high current go through, and therefore your protected device won't be suffer from this high current event. So the important feature, of course, there's several in nowadays. This TVS has been this concept for TVS used to protect for the ESD has been developed for a while. We have some more advancement in the TSP, but in general, the TSP has several important features. So this is a diode-based protection. So the diode-based protection is that we have a lower breakdown voltage here, and also during the on state, which is here, during the on state, the low clamping voltage provide a low resistance path for the excess voltage, and also this is a fast response time that can often operate with a nanosecond range, and this is a bipolar protection, both a positive and negative voltage transient. That's okay for using the diode. And then the high inrush current handling, so that means that this diode can handle for the higher sudden current. And then during the off state, the lowly current minimize the impact of during the normal operation of IC, and also low capacitance to avoid the impact on the high frequency for the IC. Also the small footprint, because it's just a single alone diode, so that will not take too much area. So that's also the good for the overall cost consideration. So therefore that's why use a simple diode for the ESD protection is a very popular method. And also here is just another slide to illustrate that what would be the general strategy for the ESD protections here. So if you look at the ESD protection, actually we can consider with respect to the several level. The first one is that in the nearby, a protection network must be device which allow ESD current to pass through the IC without causing any damage to either protection network itself or remainder of the ICs here. So here is an example. We have the certain key device here, and we all know that the most weak part for our typical MOSFET is related to the oxide. So normally we will place the ESD in front of a gate side because we want to protect our gate oxide to avoid any ESD induced values here. And also, in addition to this one, we also will do this ESD protection in this region, that's in the package level. And also, to further enhance, we will also have in the system level, as shown here. So therefore, the idea is that we will try to shunt the current away from the sensitive circuit, and also prevent the high voltage across the sensitive circuit. So therefore, if you look at the state-of-the-art ESD protection. People talk about the device level protection, even for the system level protection, because you need to protect the whole system that can avoid for the ESD issues. So in the end, this can be the very dedicated topic from the device to the package to the system for the whole solution strategy for the ESD protections. And here is some of the key requirements that if we want to have the device that can be effectively used for the ESD protection. So ideally, we want to have the high current capability, just like here. So we can use a diode as one of the example. We have the high current conduction and also the high current conduction. So the high current capability and low resistance, that's actually the very good requirement. That's a very necessary requirement for our ESD protection device. So therefore, even we can consider using the NMOS here, and also the lateral SCR here. These are all the regions that have the high current and low resistance. Because we want to make sure that once the high voltage ESD strike is happening, then this protection device can be turned on, and then can have a high current go through, and therefore we want to have this device has a high current capability. And also, it'll be great that this device has a small footprint, so we won't waste our chip areas, and also the low parasiticity, so that will not cause any frequency influencing our main device. And also, during the normal operation, if there's no ESD strike, and this is a turn off, and it must be turned on very quickly during the ESD. So we consider for this requirement for the ESD protection device. Right now we have several commonly used devices. As we already say, the diodes. And also we have another one called the grounding gate NMOS. That's we try to ground the gate. If we ground the gate, actually it will also work as a diode, as a diode transistor. And we also have this silicon control rectifier. So these are the three most commonly used devices for the ESD protection solution. So the first one, the diode. So we have been already mentioned that these two regions are the regions that we hope that our diode can be work as under the ESD, under the event of the ESD strike here. So the ESD protection diodes are connected in the reverse direction, so they do not conduct it when the voltage across ESD protection device. And then therefore we can consider that there will be the two scenarios, because the diode is asymmetric characteristic. So asymmetric means that the turn on voltage from one side versus another side is a huge difference. So you have a turn on voltage here for silicon is roughly 0.7, but this one, it will be depends on your breakdown voltage here. So therefore, to overcome, to have a symmetric of the ESD protection, sometimes we will not only consider as a unidirectional, but also we will consider as a two diode as a bidirectional. That's a diode back to back connected with each other. So in this case, we can have the symmetrical for the forward and then the ESD protection. So these both unidirectional or bidirectional ESD can be used to absorb the positive and negative ESD pulses here. So that's the typical ideas that how we use diode for the ESD protection. So here is one example that we have the dual diodes for the ESD protections. So the dual diode based ESD protection is the best known ESD protection concept for the analog IOs here. And then the ESD dual diode typically consists two diodes connected in pairs. So under the normal operation condition, the diodes are reverse biased, so they don't conduct a current here. But as the voltage exceeded a certain threshold, for example, the breakdown voltage of diode, the diode start conducting, provide a low impedance path for ESD current to flow here. So here is one example. If you have the ESD event at this moment, so you will start to have the high voltage, so the diode here will be triggered. And then once the diode here will be turned on, then you can have the current, high current go through, and therefore you won't have the high current to influence of your main device. And also, we are not only consider as we sometimes will also place several different level of the ESD protection. This is because of the, for example, the gate oxide is very sensitive during the ESD stress here. So therefore, you will be very open to see in reality, we'll put one primary ESD protection, but to make sure that they won't be damaged to our gate oxide, we also will have this secondary ESD protection. So that's an idea that we want to 100% make sure that our gate region will be damaged by the ESD events. And next one, we can also consider the MOS-based protection clamps here. And then the most well-known right now, even right now we still use, is what we call the ground gate NMOS, the GG NMOS here. So idea is that we try to place the gate as a grounded. As you see the schematic of here, we have this placed as a grounded as a gate here, and then therefore we can also use this one to consider as ESD clamping device here. And with this consideration, once we grounded the gate, actually then you will see there's this one, electro NPN transistor can be seen from here. This is a NPN BJT inside this GG NMOS here. And therefore, we hope that during the ESD events happening, then this parasitic BJT can be turned on faster than our main device, the electrode in our main device. So therefore, there's one consideration that how do we make sure that this parasitic NPN BJT can be turned on, which is equal to our substrate current times our R substrate should be larger than this turn on voltage of this BJT, right? So as long as the voltage drop here is larger than the turn on voltage of this BJT, then the parasitic BJT can be turned on, and therefore we can start to see this latch up event, and therefore the ESD strike will turn on this parasitic BJT, and then all the high current will go through this GG NMOS rather than go into in our main device here. So it's here. So in the end, you will find out that it's not that difficult to understand the ESD, the latch trap issue. Latch trap issue is mainly related to the parasitic BJT that would be self-generated turn on. But also we can leverage this characteristic that if we want to make sure that our ESD protection device can be turned on, we also use this latch trap characteristic as well. So once we have this NPN BJT, and then we just want to make sure that this the EB shunt resistance control the trigger current, so we can revise our substrate current. We can try to do some different doping, different process to change the substrate current that can produce a different trigger current. Because we need this trigger current to forward bias the EB and then force the device into the snapback condition, and therefore there will be the very high current go through this GGMOS, and then we can use this advantage to avoid the high current to go through in our main device. So also here is the full picture that if we do the TOP testing in our GGMOS, that we have seen the several different regions here. The first one is a bipolar turn on, which is here. That's a typical one that we have this first snapback. That's due to the latch trap. So that's an electrical effect. And the second, we will start to see if the current still goes very, very high, we will start to induce certain thermal issues. Which is here. So we will start to have the second breakdown. That's because due to the thermal effect destructive, that will lead into the second breakdown. This is a second breakdown. That this is a phenomenon happen in the GGMOS. So this is a typical TOP-based IV. You will see that we will not only have the first latch trap, first snapback, but we also might have the second one, which is due to the thermal effect. Also, we might actually start to consider use ACR, which is the structure that we have already mentioned before. That the ACR is has some advantage that has a lower holding voltage and also the low R here. Therefore, can in the end to have a lower power dissipation and also the high ESD threshold here. So the problem for the SCR is that there will be the high trigger voltage because you need to break down in the N well and P substrate, and also that will be influenced by the substrate resistance, N well resistance, and spacing, and also usually need a trigger current, need a trigger circuit to reduce the turn on voltage. So that's a typical concern for the SCR here. So you see here, we need to have a one trigger current, because as we already say that the purpose for the ESD protection is we want to make sure the trigger voltage for latch trap should be lower than our main device. So if this trigger voltage is way too high here, and then our main device will face the latch trap earlier than this protection device. So if we want to use the SCR, we need to have this additional trigger circuit to give a small current and then to reduce this turn on voltage here. So that's also the one of the main consideration for design the ESD protection, we want to have a lower trigger voltage, lower turn-on voltage. So here is a summary for the different protection device comparison here. So we have been talking about the dial. Of course, there are many different protection devices, and they are getting more and more complicated. But in this lecture, we'll only introduce a basic one. But the basic one is already enough to understand the purpose, the design strategy for this ESD. So we have these diodes, which is very often used, and we also have this MOS, and also the lateral SCR. These are all very often used for our protection circuit. But as you can see that there's no perfect for the each ESD protection. If you want to be the perfect, in the end you will actually design getting more and more complicated. And also most important is that you will start to need more and more chip area. So therefore, that's always the trade-off. How to make the compact ESD and then very efficient, but also will not use too much area. It's always the key research direction or the development direction for the ESD protections. So when we have the ESD event really happens, then for sure the ESD can induce several failures, and then the failures can be divided by these three different categories. The one is the direct damage, which is a hard failure. So you will see the physical destruction of the whole device. You see the complete like a burnout of your device, or partial degradation, or there could be a certain we call the indirect damage. That's a soft error. So we have this the soft error is that means that we might not see very obvious damage from the device structure or from the device image, but that's already caused several function abnormal. For example, in the case with the logic, if once we have this indirect damage, that might be cause this logic state abnormalities. So that means that you cannot have the proper logic state between the 0 and 1 and 0 and 1. That's will cause a function abnormal, but the device still looks good, but in the end you will start to see there's abnormal in the certain of your functions here. And also they can have this what we call the latent values here. So the device was weakened initially by the ESD, but we will not see the immediately failure for this device, but the device is already being damaged. Just the damage is not that high enough to see the immediate failure, but after your operation for several weeks, several months, you start to see this damage is getting larger and larger. This in the end that will cause direct damage. So that's also can be considered as one of the failure in the ESD. That's we call the latent failures. So if you consider the failure signatures here, that the HB and NN typical device damage are energy related failures. For example, like the contact spiking or thin film burn off, because of in this case the duration for the HB and NN is relatively long, and therefore we are easily to see the thermal induced failure, which might have this contact spiking and also the thin film burnout here. And the CDN typical device damage like the oxide damage, which can be caused as gate dielectric, gate oxide breakdown, and also several other phenomenon can be also happens, which is mainly due to the high speed and high current nature of the CDN discharge here. So that's why normally we can expect the CDN can show the different value mechanisms compared to the HBN and NM. So now we will start to look at what would be the future challenge of ESD. We have been going through the very basic part for ESD, from the fundamental understanding what is the lecture event and what would be the ESD testing standards, and then the testing method for TOP, and then we also talk about the protection for the ESD. So we talk about the several possible devices that can help us to avoid ESD failures, but still there will be the huge challenge if we do the technology scaling. So basically, as we already mentioned, that once we do the scaling, we try to scale everything. We not only scale the front end, we also scale the back end. So we will see the getting more and more serious of the reliability issue. And then also, once we have this technology scaling, we will see that this also will limit it for our ESD protection, which is mainly due to the breakdown also is getting small. So this is a case. For example, this is oxide fail versus a different technology node here. So we can see that as we scale to the advanced node, of course our oxide is getting thinner and thinner. Therefore, the voltage that can lead to the oxide breakdown is also reduced, and also the current handling capability, because now our pitch size is reduced, our contact hole is reduced, therefore the current density is higher, but we cannot handle such high current as we have before. Therefore, we start to suffer for these ESD challenges. So you can see this is a TOP versus a different technology, and then we can start to see that with technology scaling, the voltage trigger is reduced, and also the failing current is also reduced as well. So the ESD design is window is shrinking with scaling. Because of now, as our technology is getting with advanced node, our breakdown voltage is reduced, and therefore it's easily to trigger the latch trap in our main device rather than just the ESD event in our protection device. So this is because of the reality, the ESD event, the breakdown voltage for our device is reduced. But the problem is that the real world ESD event don't shrink. So that means that our device still suffering for 2000 volt, 4000 volt, 6000 volt ESD strike, because that's due to the triple electricity. So this phenomenon still existing and doesn't shrink, but the problem is that our ESD design window is a shrink with scaling. So that poses some of the additional challenge for the ESD design. Okay, so here is some of the reference list that you can try to look at. There are many online literature, videos, and then also the academic paper talk about the ESD. So in this lecture, we will only go through the basic one. We talk about the phenomenon, typical standards, and also some of the basic device we can use for the ESD protection. And of course, there are some more, because this is the knowledge that has been accumulated for the last 2 decades. So there are tons of literature try to talk about this issue to improve this issue. So if you are interested in, you can look up further by yourself. Okay, so that's a final will be the summary for this the ESD issues here. So in this lecture we talk about the ESD, which is a fast and high current reliability threat, and sometimes happening below 200 nanosecond, but with several amp or even higher current. And this can cause a dielectric breakdown, thermal damage, junction burnout, and also sometimes has this what we call the latent values here. And this ESD generation is not be possible avoid in the real environment. It's because due to this triple electrical charging, that's pretty depends on our material, humidity, surface, and motions. And although for the human we will not detect for ESD below 3 kilovolt, but 3 kilovolt is enough to destroy our IC. So you will sense the ESD shock, but that's ESD already enough to destroy your ICs. And the main reason that the ESD will cause the issue is because of this electrical event here, which is due to the parasitic SCR problem here. This triggered by high current or high voltage, and we have this regenerative PNPN actions, and in the end that cause a very large current here. And then we need to have certain isolation, guarding, or proper biasing to avoid this lecture. So understand the discharge physics is essential, and also the ESD reliability is not equal to the pure DC stress, because the ESD is a combination with the current driving, transient, and then the high speed event here. And then also the value signature is a difference compared with the different models. We have the HBN is mainly related to the energy, and CDN is mainly related to the speed here. And we also talk about the several models already, so that's related to the HBN, NN, and CDN. And also we talk about the TLP, which is essential to characterize the ESD protections here. So that's give us a very clean and repeatable high current pulses that can very good for us to do the ESD stability diagnosis. And the idea for the ESD protection strategy can be summarized as a one sentence: is we just want to control the high current path. So we want to make sure this high current path will not directly flow into our main device, and we want to make sure this high current path will flow out from our ESD device here. So we have introduced several different devices very often used: diodes, the GGMOS, or the SCR, or even the diode trigger silicon control rectifier. That's we need to as a small trigger circuit. And also this protection requires fast turn on, low clamping voltage, high current capability, and low parasitics here. So that's a general requirement that for this ESD protection device. And also for the future, the scaling increase the difficulty for our ESD protections. For example, the outside breakdown voltage is getting lower, and also the second breakdown for the GGMOS will also decrease because our device cannot handle such high current, and also the cell pitch is reduced, and everything is reduced, and thermal is increased, and therefore it's easy to get a thermal related hard breakdown. And then the main issue is that the real world ESD event do not scale. We don't see any reason why the ESD voltage from real world won't decrease. Still will be the several thousand volts, sometimes even higher. But the problem is that our ESD design window shrinks, so that keep posing the ESD as one of the key research in the reliability fields. Okay, so that's the end of our chapters here.